Hey everyone, so this is the last video where we're going to talk about a little bit more about the Carnot cycle and how it relates to heat and work. So um, this is the second law of thermodynamics. So we were kind of talking about some of the other laws. The second and third law are kind of the same thing, but the whole idea about the second law is pretty much some of the stuff that we've been talking about that basically it is impossible for any cyclical process to be essentially 100% efficient. That it's impossible for us to extract some amount of heat and turn that completely into usable work. Um, this description basically kind of talks about what we kind of mentioned before about how we have a scenario of like a engine working into a fridge, and basically it kind of says that um, it doesn't work. It ends up breaking the law of entropy always having to increase. So that's pretty much what this is saying, that it's not something that's completely that's at all possible. We'll always have some sort of exhaust heat coming out. All right. Now, moving on. So one thing that's important, mainly for these processes, is that the amount of work or the amount of heat that we get is solely dependent on the path. So it's not about where we start and where we end, but how we get to those two spots. Are we going to those two spots through an adiabatic process or an isothermal process? So it's very path dependent. Um, so yeah, this just kind of says again, restating a lot of the same thing, that if we assumed that it wasn't path dependent, then that means that if we start and end at the same spot, then there would be no network or no net heat bringing us there. So the fact that going from doing a isobaric, isovolumetric, isobaric, isovolumetric back to the same starting point, um, there's going to be a net heat and work. But if we assume that the path didn't matter, whether it was isobaric or isochoric or isothermal, that all of them had the same values, then we'd end up getting nothing. Um, yeah, so you may have noticed us using this special symbol. This is mainly due to the fact that there's a slight change in when we do the differentials for Q and W, basically stating the fact that these are path dependent works and path dependent heats. And as it says here, this is actually much closer to what we would normally expect as like the heat difference between um, the two states and things like that. All right. So we can actually come up with an equation to kind of look at what's going on with like the irreversible process, the work done through an irreversible process versus the reversible. And it's pretty much the same thing that we did last time. So if we assume that the two cycles are operating at the same exact temperatures and they're starting at the same initial spot, then it doesn't matter which one we're talking about. They're the change in their internal energy will end up being the same because again, those are temperature dependent variables. Uh, but we also know that the irreversible efficiency has to always be strictly less than the reversible efficiency. So from here, we can actually make this claim. We can make this claim because if we play around with the whole irreversible and reversible equations as they relate to work, we'd end up getting this relationship. You know, the fact that, yeah, so the change in internal energy, again, is always going to be the sum of the work and the heat. So we can set these two equal to each other. And that means that if the irreversible work is strictly more than the reversible work, then the irreversible heat has to be less than the reversible heat. That's pretty much it. So, pause video, work on the stuff, and we'll go over in a second. All right. So they kind of want us to show this for a free expansion. So what we're going to do is, if we look at the work done by a gas during a reversible process, we know it's equal to this, and we know that when it's work done on the gas, we know it's got to be negative, and we know that the work in the irreversible process is 0. So from there, we actually know that the work done by the reversible during a reversible process has to be less than the irreversible process. So basically, we just kind of have to show that. So, um, and then the next one, they want us to the heat transfer to the system. Again, because of the free expansion and the fact that it's a reversible, well, for the reversible isothermal expansion, we know that the change in internal energy has to be the same. So the heat and the work have to be equal. So from here, we get this. We get that the Q reversible is going to be some positive number based off of the fact that it's going to be the negative of this, and because it's going to be greater than 0, it's going to end up being greater than the irreversible process. All right, so this is, we can kind of relate the work again back to the whole Helmholtz free energy. If you remember, the work, this is that first law that we keep using. But if we kind of go back to our previous definition of what dq is, um, then this work actually is, by definition, the Helmholtz free energy. And again, this is something that we had said before, that during the isothermal process, these two are going to be equal and opposite. Um, so for the isobaric case, where the pressure remains constant, we can also find the work. Um, we do this by basically coming up with two different definitions of the work. So what we have to do is actually take into account the external effects of the work that are actually added to the system. And this comes up with basically an effective work, like taking into account everything. So if we use, once again, the first law equation in for this, putting it all together, we end up getting defining this new term right here, which we actually refer to as the enthalpy. So this is something that you've probably heard if you've taken a chem course. Um, it says here, but it's pretty much kind of like the Helmholtz free energy, but for heat rather than for work. So the Helmholtz free energy kind of tells you how much usable work energy you have. Enthalpy kind of talks about or deals with how much usable thermal energy do you have. All right. So the way they use U is being used as always as the internal energy. This PV is pretty much the amount of work needed in order to move the atmosphere away for the system to actually exist. So, pretty much the same thing as what we would normally expect what PV represents. Yeah, so again, this kind of says that if we set them, that in this one specific case where the pressure remains constant and there's no real work being done, then we do end up getting that they are equal. Like I said, they're related to each other, they're similar to each other. Um, so this one's talking about an isobaric process that's also isothermal. And it is just another uh, definition that we can come up with, the Gibbs free energy. And again, it's a how much usable free work can we have, or effective work that we can have under the scenario where we have constant temperature and constant pressure. So again, somewhat still related to free Helmholtz free energy, but with a little bit of extra stuff. So again, these are things that you probably would see and know about when you take a chem course and you talk about the thermodynamics in those classes. So just really quick practice with this stuff. Pause video, work on the self. We'll go over in a second. All right, so they give us this scenario of water being decomposed. So I'm going H2O to H2 and O2. So to figure out the effective work, this is pretty much just going to be the difference in the Gibbs free energy of all objects. And that's it. All right, next question. Pause video, work on the self. We'll go over in a second. All right. So they want us to figure out this the voltage needed in order for this electrolysis to occur. So voltage. This is just the basic definition of voltage, based off of the electrostatic concept of it's the defined as the amount of work needed to move a charge. So we plug in the numbers that we got, and we get 1.23 volts. Um, so once again, we can, if you recall that we had that slightly elongated um, the thermodynamic identity equation, the one that included the chemical potential part. If we pretty much do this and we relate these two together, then that means that these terms, because the dq and the tau d sigma are related, they're together. So that means that this entire section is being related to the work. Now we know that this is, as they say, mechanical work, physically moving particles away. So we can actually define this term as being the chemical work. Again, pretty much the same thing that we've been doing with a lot of this stuff. So with the chemical work, it's moving particles in and out based off of um, essentially concentration. So when we find the chemical work, it's going to be the sum of the chemical work of the two systems. And because of the fact that this amount of particles that one system gains is equal to the amount of particles one system loses, we can actually combine them to look like this, taking out the dn from each term. And it ends up just being that the difference in their chemical potentials times dn. So pause video, we'll do this real quick. All right. So they want us to figure out the amount of chemical work done per particle. So all that is just the difference in their chemical potential. Now, what we'd want to do is go back to our definition of what chemical potential was. Remember, it was tau ln of n over nq. So we put that in for system 2 and system 1. Moving some things around, the nq's end up dropping out, and we end up getting this tau ln of n2 over n1. And then for part B, they said that they want this to show that this is equal to the mechanical work per particle. So what we're going to do is use the equation that we have for mechanical work. This is a yeah. So what we would do is use the integral PdV. Oh, there it is, isothermal. I knew it said isothermal somewhere, I just couldn't find it. So we use PdV, and then we use the ideal gas law in so that we can actually integrate this, and we end up getting this. This is, again, this is the standard work equation for an isothermal process. But for here, what we'd have to do is actually rewrite, because we don't know what the volumes are. So we'd have to rewrite the volumes using the concentration. So we'd use N1 times over little n1 concentration in for V1. So when we do that, we can actually find that we'll be able to cross out N1 and N2, and we end up getting this. And then dividing this over to get the work per particle, we end up getting the exact same equation that we got last time. And that's pretty much it. So here are a bunch of the things that we talked about. We kind of talked about how we'd find like Carnot efficiencies of processes of the heat engines and fridges and all those things. And then we also brought in some definitions that, like I said, you probably see later on in other thermal classes, things like the Helmholtz free energy, Gibbs free energy, and all that stuff. And we also kind of made a slight definition of what chemical work was. And then this is your last homework question. So you're not going to do all of question 1 and 2, just the parts that they mention here. If you have any questions, let me know. Otherwise, I'll see you later.